Welcome to today's Explainer. We are taking a virtual field trip straight up into the sky to explore the invisible blanket that is literally keeping us all alive. I'm so thrilled to be your guide today as we unpack the incredible science behind Earth's atmosphere. We walk around every single day completely submerged in this ocean of gas, and we totally take it for granted. But without it, our planet would just be a lifeless, freezing rock, constantly bombarded by radiation and space debris. Here's our flight trajectory for today. We'll start with a look at Earth's invisible protective blanket, then climb through the troposphere, the stratosphere, the mesosphere, and finally into the thermosphere and the absolute boundary of space. All right, let's jump right into Section 1, Earth's invisible protective blanket. As a science teacher at heart, I always like to begin with the basic building blocks. Like, what exactly are we breathing right now? Well, it's actually a perfect mix. The vast majority of it, 78%, is nitrogen. And you know what? That nitrogen is doing us a massive favor. It acts as a relatively inert diluter. Think about it. If our atmosphere was pure oxygen, even a tiny spark could cause a massive, unstoppable fire, because combustion just isn't possible without oxygen. Oxygen makes up about 21%, which is the perfect amount to fuel our respiration. And that remaining 1%? That holds trace gases like argon, plus absolutely crucial variables like carbon dioxide and water vapor, which work together to regulate the Earth's temperature. Now, as we journey through this full stack of atmospheric layers, you're going to see how the atmosphere isn't just some uniform soup of gas. It's actually highly structured. It's almost like a giant layered cake, bounded by these invisible pauses where the temperature and the chemical composition suddenly shift dramatically. Moving right along to Section 2, Troposphere, the weather zone. The troposphere is the densest layer of the bunch, and it acts as the main stage for all of our weather. I'm talking everything from gentle morning fogs to massive thunderstorms. It extends about 8 kilometers high at the poles, and it bulges way up to 18 kilometers at the equator, simply because heated air rises. Now, because gravity is constantly pulling gas molecules down toward the Earth, 80% of the atmosphere's total mass is squished right into this bottom layer. And crucially, it holds 99% of the atmosphere's water vapor. Literally every cloud, every drop of rain, and every snowflake you have ever seen in your life was born right here in the troposphere. Okay, I literally love teaching this part. It's so fascinating. As you climb higher in the troposphere, the temperature drops very predictably, by about 6.5 degrees Celsius for every single kilometer you go up. We call this the environmental lapse rate. And this is exactly why the peaks of super tall mountains, like Mount Everest, are constantly covered in freezing snow, even if the base of the mountain is sitting in a warm tropical climate. As the air gets thinner up there, it just loses its ability to hold on to heat. So that begs the question, what happens when we punch right through those clouds and leave the weather behind? Well, as we continue our ascent past all that turbulence, we enter a completely different environment. We cross this invisible boundary called the tropopause, where the temperature actually stops dropping, and we enter layer number 2. Let's dive into Section 3, Stratosphere, our solar shield. Welcome to an incredibly stable layer extending up to 50 kilometers. This is actually where commercial jets like to fly to avoid turbulence. Because there's virtually zero water vapor up here, there are almost no clouds or weather to bounce you around. But hey, it's not just offering us a smooth flight, it's performing a critical, life-saving function. I'd like you to meet ozone. This is a molecule that absorbs 97 to 99% of the incoming UVB radiation from the sun. Ozone is really just oxygen, but instead of the normal 2 atoms we breathe, it has 3. That extra atom makes it highly reactive but incredibly effective at intercepting the sun's harsh ultraviolet rays. And here's a cool fact. When the ozone absorbs this UV energy, it actually heats up the stratosphere. So completely unlike the troposphere below it, the stratosphere gets warmer the higher up you go. Now, it is absolutely vital to understand the difference between the good ozone high up in the sky that protects our DNA and the bad ozone down near the ground. Up in the stratosphere, ozone acts like planetary sunscreen. Without it, that intense UV radiation would rapidly damage our skin, mutate our DNA, and completely destroy our crops. However, when ozone forms down here near the surface, which usually happens as a byproduct of pollution and smog, it acts as a really harmful respiratory irritant. So the main takeaway here, we definitely want ozone high up in the sky, not down in our lungs. Okay, so we're safe from sunburns and radiation, but what about the millions of literal space rocks hurtling toward Earth? Every single day, our planet is sweeping through tons of cosmic debris. So why aren't we constantly dodging meteorites on our way to work? That brings us to Section 4, Mesosphere, the meteor burner. Moving into what I like to call our planetary Kevlar vest, the temperatures plummet to a freezing -90 degrees Celsius. That makes it the absolute coldest part of our entire atmosphere. Since we are far above the ozone layer now, there's nothing up here to absorb the sun's heat. The air is becoming incredibly, incredibly thin. But actually, there are just enough gas molecules left to stand guard. Because despite that freezing cold, these super thin gases perform a miraculous feat of planetary defense. When a piece of space rock slams into the top of the mesosphere at tens of thousands of miles per hour, it dramatically compresses the air right in front of it. This intense compression and the resulting friction generate massive amounts of heat. This melts and vaporizes the rock long before it can ever reach the ground. So next time you look up and make a wish on a shooting star, just remember, you're actually witnessing the mesosphere successfully protecting the Earth. And finally, Section 5, Thermosphere and Beyond, the Space Boundary.
At exactly 100 kilometers above sea level, we cross the Kármán line. This is the internationally recognized boundary where aeronautics officially ends and outer space begins. At this altitude, the air is less than 1/millionth the density of sea level. Conventional airplanes simply cannot fly here because there just isn't enough air to generate aerodynamic lift. Up here, orbital mechanics completely take over.
Now, here's a complete paradox for you. Surprisingly, while extreme UV absorption causes temperatures to skyrocket up here to around 2,000 degrees Celsius, it wouldn't actually feel hot to your skin. Why? Because the air density is near a total vacuum. The term thermosphere literally translates to heat sphere. Molecules of oxygen up here are absorbing high-energy X-rays and extreme UV radiation, causing them to vibrate at incredible speeds. And that vibration is exactly how we measure temperature. But here's the catch. Because those superheated molecules are spaced so incredibly far apart, sometimes there are literally hundreds of kilometers between them, there just aren't enough of them to actually transfer heat to an object. So if you stuck your bare hand out the window of a spaceship in the thermosphere, it would freeze instantly, not burn. Mind-blowing, right? And this layer is just buzzing with activity. It allows for global radio transmission and creates the stunning auroras near the poles. The lower part of the thermosphere contains something called the ionosphere. Up here, solar radiation strips electrons away from atoms, which creates a whole layer of electrically charged particles. That charged layer actually bounces AM radio signals right back down to Earth, allowing them to travel way over the horizon. It's also exactly where charged solar particles collide with gases to paint the sky with the breathtaking northern and southern lights. And, for sure, it's the exact zone where the International Space Station is orbiting our planet right now. And for our grand finale at the very, very edge, we have the exosphere. This marks the quiet transition where our protective blanket slowly just dissolves into the void. This layer extends thousands of kilometers out. The gravity here is so unbelievably weak, and the particles are so highly energized that the lightest elements, like hydrogen and helium, literally just float away and escape into deep space. You see, the atmosphere doesn't just hit a brick wall and stop. It gently fades away, becoming totally indistinguishable from the solar wind. From the weather-making troposphere to the meteor-smashing mesosphere, our atmosphere is a brilliantly structured cosmic shield. So I want to leave you with this thought. Next time you step outside, will you just see an empty blue sky? Or will you see the multi-layered, invisible shield working tirelessly every single second to keep you alive? Keep learning, keep looking up, and we'll see you on the next Explainer.